the experiments. So which are those experiments we are going to perform during your school. So we'll talk about in details about that. So basically there are 4 experiments what we are going to do here during this school. So yeah, I myself Jameer and along with that Ashish is here, Desh, Prakash, Subhashis. We are going to assist you to do these experiments. We are going to conduct these experiments. Okay. So we'll just go one by one. Yeah, these are the 4 experiments what we are doing. So effect of putting a reflector at the back of an antenna. So how it's going to affect? We are going to see using different set of instruments. So in 2 ways we are doing this experiment. So I will explain about that in details. And the second experiment, Johnson noise. So you might have heard about the noise, and Johnson is a thermal noise. So we are going to study about that. And the third experiment is detection of H1 line, okay, from the Milky Way or the galactic plane. And the fourth experiment is the sun experiment. So basically you're observing the sun using radio waves. Okay, so these are the 4 experiments. We'll see one by one. Yeah, so we'll see about the first experiment. So the effect of putting a reflector at the back of the antenna. Okay, so in first lecture, in the previous lecture, Prakash have explained how antenna works and all. So what we are doing here, so we are taking an antenna, okay, and we are radiating from an antenna. At the other end, there is another antenna which is receiving the power. So there are 2 antennas. One is the transmitter, and the second is the receiver. So what happens when, if we put 2 antenna across this, and one is radiating from the one side or the other end, and second is receiving at the other end. So basically, when we take away from this, and when we are taking away from like the transmitter side, so you will start to noticing this, the power or the uh, the receiving power will start decreasing by 1 by r square, the inverse square law. So we know that. So what if we put a reflector at the back of the transmitting side? Okay, so based on at what distance the reflector is kept. So based on that, so whether it will be a instructive interference or destructive interference, we should be able to get the more power at the receiving side. So what we are doing here, so basically this experiment was designed during the COVID, so that this experiment, yeah, Akash knows it better because he was in previous winter school. So using cell phones and laptop, you can do this experiment. The cell phones were acting as the transmitter, so by creating a hotspot, and at the other end, receivers, you can take another cell phone, a smartphone, or a laptop, where you can measure the power. Okay, so we right now we are slightly modified this time. So there is an antenna, dipole antenna here. You can use at the transmitter, and at the receiver, you can use the another type of antenna. It could be a dipole or it could be alveolar, and you can receive and measure the current. Okay, so if you're measuring the power in laptops, it should be in dBm, and if you're using the other set of instrument, so like antenna, Yagiuda or dipole antenna, then you should be able to measure that in current, in microampere. Okay, so we need one smartphone or the 2 smartphone. One will be at the transmitter side, and the second will be at the receiver side. And if you're using the laptop, then the laptop can be used at the receiving end. Okay, and you need a measuring tape to measure the distance. So these are the hardware you need for this experiment. Okay, so right now we are keeping an antenna here, right? So this is basically a transmitting antenna. So this is a simple dipole antenna. So we are giving some current. So it is radiating in these 2 directions. Okay. So after putting this antenna, so there will be an imaginary antenna here. Okay, which is the reflection. So it's a simple optics. Okay, and the power which is transmitting at this end will be the combine of these two antennas. So based on at what distance you are keeping, at what wavelength you are keeping, so it will be constructive or destructive interference, and that will be received at the other end. So this is simple, a block diagram you can say. So about this. So what we are doing, we are keeping a transmitter here. It could be a cell phone or an antenna, and we are keeping a reflector. It could be a metal sheet, or we can take a cardboard, or we can paste aluminum foil or any other foil. So it will be act as a metal plate. Okay, and then we are changing the distance from the transmitting antenna, and at the other end, at the receiver side, we are measuring the power which is transmitted by the transmitter antenna. Okay, so these are the hardware. So this is basic setup what we used in our previous. Now we are slightly modified it. Okay, so instead of cell phones, what we are doing, we are keeping the antennas here. Okay, and here we are using a metal sheet. Okay, copper metal sheet, and here we are using the cardboard, which is on the cardboard we have pasted the aluminum foil. Okay, so what should be the size? So it's like few times of the wavelength. So you can take any metal sheet or cardboard which is the aluminum is pasted on that. So few times of the wavelength you are operating at. So if you are operating using these cell phones, so if you are operating at 2.4 gigahertz, then what will be the wavelength? Which will be around 12 centimeter, right? Okay. Around 12 centimeter. Okay, and in case the other setup, we are generally operating around like between 500 to 900 megahertz. So this is the basic simple setup. And what is the procedure? So first we need to create an hotspot. Okay, and then we have to like uh, connect to the receiver using that hotspot. Okay, and then we have to make sure where is the physical like position of the antenna in your cell phone as well as in your laptop, so that it will be easy for us to measure the distance between the receiver and transmitter. So basically we are not measuring where the mobile is kept. Basically we have to measure from the antenna to antenna. So that will be your distance, and the antenna to the reflector. Okay. So those are the kind of uh, the, there are like things we need to know, and like so I have explained few of them. Then move the reflector slowly away from the transmitter side. Okay, and see at what distance you are getting the peak or the falls in the power. Okay. So yeah, I have already mentioned to find the physical location of the Wi-Fi antenna and keep mobile laptop fully charged, that so that like during this experiment it should not drain it should not go out of power. Otherwise the whole setup will be disturbed, and probably you may not be able to get the similar like result if you start again. Okay. So, and a lower limit should like if you start doing it, if you're getting less than 80 dB of the power, then you should stop there. Okay, so you should not continue more after that, because your receiving antenna may not be sensitive to detect after that. If you're getting less power beyond 80 dB or 90 dB, your antenna is not that sensitive to recognize it. So that's why we have to make sure if you're getting between 80 to 90 dB or 95 dB, then you should be able to stop that. Okay, so there are a few more tips. So make sure the data connection is in offline mode. Okay, so why? Because if you keep your cell phone data online, so you're also receiving the packages. Okay, and that may add like power to the transmitting signal. Okay, so because of that packages, the power may fluctuate, and we don't want that. Okay, so we have to make sure that either it's in a flight mode or the power data should be off. The data mode should be off. Okay, so remove smartphone cover if you have anything, and sometimes these covers are made up of metals, and we should avoid that because those are good reflectors as well as absorbers. And we have also need to take care. We should not be very close to the setup because we ourselves also might be reflecting those signals. Okay, so that's why we should be away from this setup. So whether it's either in the transmitter side or the receiver side. And whenever we are taking observations, so we should not also move between the setups or across the setups. And we also need to take care, there should not be any major walls because these walls are also good reflectors. So basically this whole experiment need to be done at the outdoor. Okay, so we are doing this next to the lab where we have an open space on the terrace. So we are going to do the experiment in that premises. And this experiment can be also done at your home or wherever you are staying. So it's not like that this is completely has to be done in the lab. Okay, so basically, so when we designed, so we kept in mind, so it should be done at the home. So this is the observation table. So you can note down at the interval of 2 centimeter power either in dBm if you're like using a laptop or cell phones, and if you're using antenna setups, then you should be able to get reading in microampere. Okay, because we are measuring current. So at the end, like you should be able to get such similar result. So wherever there is a constructive interference, you should get peak. Wherever you see the destructive interference, you should get uh, less power. Okay. So about the software, if you're using cell phone or laptop, so these are few software which you should be able to get online. These are open source softwares, okay, and you can install in your like laptop or cell phones, okay. Wireshark is basically for all all the operating system, but we recommend it for Mac, and for Windows we recommend the Wisdombler software, and for Python script, so Prakash has written the whole script for Python based. So we have also that. We'll share the link. And Wi-Fi analyzer for Android smartphone or the Apple handset have this software. So these are the few resources and the reference. Anyway, we will share this presentation with you. I will share with you so that in case if you don't find anywhere, so you can refer. So we'll come to the second experiment. Any doubt about the first experiment? Yeah.
Finally, when we perform this experiment,
Huh.
are we going to use the tablet and mobile or laptop or
So this experiment we are modified. We are basically doing with the antenna trader kit. So there are antennas. So we'll do that, and during free time you can also do the same experiment using your cell phones and laptops. So here we will use the antennas basically because when we use these devices, laptop or the cell phones, so it takes a lot of time to settle down the readings. So when we change the distance, we have to wait for 5 to 10 minutes. So it will take a lot of time. So that's why we have like slightly modified the experiment using different set of antennas, so that like you will get this answer. But you can do it using anything. Okay. So yeah.
small d has to be done by 4.
So you find out what should be the wavelength and where you get the maximum peak. What will be the like you can also check. So at what wavelength it's operating. So the second experiment is Johnson noise experiment. So basically what we are doing here, we are studying about the noise. So what is the noise? Anything which is unwanted. So, so we face a lot of noise in our electronic system, right? So whether like it could be any electronic system. So whether it's for like doing experiment, whether it's for like getting data from any instrument, whether it's optical, radio, X-ray, it could be anything, right, in terms of astronomy. So at that time we have to deal with this kind of noise. So specifically we are studying about this Johnson noise. It is also called as Johnson-Nyquist noise. It is also called as the white noise. It is also called as thermal noise. Why it is called as white noise?
Uniform. Is it uniform in all?
Yeah. Any other answer? Because white light is consist of all colors, all wavelength of frequencies. Yeah. So this noise you can see all sort of wavelengths from the lowest to the highest. It can go from 0 to infinity. Okay, so that's why it is called as white noise. And it's very random. And you can't predict what will be the wavelength you see at the next moment. So that's why it is also called as white noise or Johnson noise, Nyquist, Johnson Nyquist, because Johnson was the first person in Bell Lab who was studying about this noise, and the Nyquist derived the whole derivation, and he came up with a systematic investigation of this noise, and he said it's not only depending on the few parameters of an electronic system, like resistance is there. If you see any electronic equipment, it consists of passive elements, right? So it is made up of resistance, capacitance, and inductor, and all of them have the resistivity. Okay, so he also saw it is dependent on the bandwidth, resistance, and the temperature, because this is called as thermal noise, right? Which directly depend on the temperature. But along with that, the Nyquist showed it is dependent on the Boltzmann constant that he came up after doing a lot of experiment and the calculation. He showed. So that's why it is also called as the Johnson-Nyquist noise. Okay. So this is basically the setup of the whole experiment. So whenever we see there is any change in the temperature, the change in the bandwidth, change in resistivity, we should be able to see there is change in the total power or the voltage at the output. Here in this experiment, so if you go through the block diagram, so there are different blocks. So one is the low level electronics and second is the high level electronics. These are the major, the two blocks of the setup. So here in low level electronics, what we are observing, we can change the resistance value for what we are going to study. The noise which is created by resistance, we are going to, like we are able to change here. We can control that. We can select the different level of different value of the resistor, and we can study noise which is generated by that resistor at the output. Okay, in low resistance we could do that, and there are amplifiers. Okay, but those are fixed. So there are two amplifiers which has a gain of 6 and which has a gain of 100. So the total gain will be 600, and after that the output of the low level electronics is connected to the high level electronics, where we have different control of bandwidth. We can select the different bandwidth, and we can again change the gain of the whole system. And then we have a oscilloscope to observe how the noise is like present and how randomly it is moving. And we can check whether it's saturating or not. And using DMM, digital multimeter, we can measure the output. So this is the low level electronics. Here you can see there is RE. So this is the input resistance where we can change. It starts from the 1 ohm and it can go up to 1 mega ohm. Okay, and we have RF, and here is the primary amplifier which has a gain of 6, and this is the secondary amplifier which has a gain of 100. So the total gain will be 600. and from here we take output and we connect it to the output of the high level electronics. So this is the high level electronics where we have two filters. So to make a band pass filter, we need two filters. One is high pass filter and one is low pass filter. First we need to connect to the high pass, okay, and then the low pass, then it will form the band pass filter. What if we change it? So first we connect to the low pass and then the high pass, what will happen? It's a band stop filter. It will act as a band stop filter. So it will stop those frequency and it will allow the other frequencies. So first we need to connect to the high pass filter, then the low pass. Okay, you can select different set of frequencies here. Okay, you have provision to select. And sorry.
Low pass filter.
Yeah.
Not band stop.
So after that, we can connect this to the amplifier. We can increase the gain to amplify. So basically, we can like select gain from 10 to 10,000. We can go up to that, and after that we have a multiplier. Why we need a multiplier? So that we can see voltage. It's not V square. And the second thing is, so this noise goes in positive and negative direction. If you average for a long time, it will be 0. So that's why we are squaring it. Once we square, then there are no negative terms, right? So we are multiplying by itself, and we are taking output at the DSO as well as on the DMM, where we can measure the voltage. So this is the basic setup for this experiment. Okay, so again there are 3 sub-experiments in this. So first we are just quantifying it and observing how noise is present in this resistance, how noise is created in that resistance. You can change the value of resistance. You should be able to see it's also changing at the output. If you increase the resistance, then the power should be more, right? And even when you control the bandwidth, when you reduce it, narrowing, you will be able to see there is also less amount of frequency on the oscilloscope. Okay, and the second is we will see how it is depend on the resistance. First, we are just observing it. We are saying and quantifying it. And the second experiment will change the resistance value and keep the bandwidth same. And at the same time, we also note down the temperature because we don't have control over the temperature. So wherever there is a change in the temperature, we'll note it down. Okay. So and the third experiment is we'll also see how it is depend on the bandwidth. We'll keep the resistance value same and we'll change the bandwidth. So these are the 3 sub experiments. So this is the like how you should be able to see the noise. Okay, in the first experiment. And in the second experiment, you can like make a table like this, and you can take observations for different resistor, and you can measure the observed output on the DMM, and you can calculate based on the bandwidth you selected and the value of resistance, what should be the noise. And this is something the graph you should be able to get. Okay. So then in the third experiment, sub experiment, what you are doing? So you are selecting the low pass and you are selecting the high pass, and what will be the effective band pass? You can note down, and this is the observed value and the calculated value. You can compare this two. So when you plot the graph, the voltage versus bandwidth, so you should be able to get something similar to this. Okay, your result should be similar to this. Yeah. So this is about 2 experiments.
So this is the basic setup of the experiment. You have a horn antenna uh, connected with the front end electronics, which is basically a low noise amplifier followed by a band pass filter, and then a long coaxial cable which comes to a receiver and a computer where you collect the data. So this is the block diagram of the experiment. This antenna is kept on TLC building rooftop, so those groups will have to come to the rooftop for this experiment. So there are a few requirements for this experiment. So to point the antenna in a particular direction, we need the azimuth and elevation of the antenna. So that we are doing using this Sat Finder app, which will basically tell you where your uh, mobile phone is pointing, and you can put it at the back of the antenna and you can turn the antenna. So first set the azimuth and then the elevation. So here don't worry about the language here. The language when you install it will be in English. Since I got these images from Google Play, it is in some other language. So this takes care of the pointing. So we'll be taking measurements in the galactic plane. So we'll be pointing the antenna in different directions in the galactic plane, and we'll look at the hydrogen line.
Windows it?
Yeah, so other requirement is at least one of you in the group should have this installation. If nobody can do it, we can provide the laptop, so don't worry. But this is basically to collect data, you have to install the receiver driver. So that requires, in a group, so we tried this, it works only on Linux and Mac system. If you don't have, in a group, if you don't have Linux or Mac system, we can provide the laptop. But you need basically these two libraries, and then you have to install the software driver for Linux system. So we'll share this presentation with you, so you'll have all the links and all the commands. There are few more things that you have to do if you are using Linux. You have to blacklist this driver from, because once you connect the receiver, your operating system will detect it as some device and it will not allow some other program to get data from that device. So you basically blacklist the kernel driver and then it will work through your command window. On Mac OS, it's straightforward. Just you need to install Mac ports and then one command. You will be ready to go.
Copy to something right away.
Yeah. So how to use the receiver? So this red command that you see, this is the command that you will be using. So the basically the driver is basically RTL power. Dash F is the frequency. Here it is some different frequency, but we'll be tuning it from 1418 to 1422 megahertz. So if you remember from the morning lecture, the hydrogen line frequency is 1420.4 megahertz, and we give the bin size as 4 kilohertz. Bin size is basically what frequency resolution you want in this entire band. Then we set the gain of the receiver dash G, which we can set it to maximum you can go is up to 50 dB. Then comes the integration time, how long you want to integrate the signal, because the signal will be buried in noise. You will have to integrate it for some duration to reduce these random fluctuations and get some proper line profile. So you can go from maybe 1 minute to 5 minutes, but not beyond that, because then the sky starts, basically it shifts by some degrees. So, but more than 5 minutes is not required. -1 here is basically for one single short measurement. If you don't put -1, it will basically keep recording continuously. So we don't want that. We just want one plot. Here dash C 80%. That is basically cutoff given for this spectrum. So, okay, to explain this command. Yeah. So actually, the receiver is the sampling frequency of the receiver is by default 2.5 mega samples per second. So the bandwidth that you will see is 2.5 mega samples per second. It's IQ sampled, so you will get this bandwidth. So real-time bandwidth of the receiver is 2.5 mega samples per second. But we are going to look at 4 megahertz worth of bandwidth. So the way to do that is basically take two measurements, one at a lower frequency, one at a higher frequency. So dongle cannot see, or the receiver cannot go to, like, in a single shot, it cannot go from 14, 18 megahertz to 14, 22 megahertz. So what it will do, but what we can do is we can basically shift the tuning frequency, take another measurement, so we get 4 megahertz worth of bandwidth. But other problem here is that there is a, at the edge of the this receiving band, there is a huge attenuation. So the sensitivity of the receiver is not good here. So what we are telling the software is basically take only the 20% portion, central portion of the spectrum, and ignore the 80% that is low sensitivity region uh, of this plot. But this is a very small window, and we want to measure 4 megahertz band. So we'll have to tune it repeatedly. So it will basically plot something like this. So it will take only the most sensitive part of the receiver, and then it will shift, and you will get 4 megahertz worth of bandwidth. So you will understand what I'm saying when you look at the plot. And then you save it in a file. Here, for example, I have given a name ground.csv. You can give any name, but keep in mind this command will override your previous file. So if you are taking a new measurement, change the name of the file before you take the new measurement. Yeah, so this is what happens. So this is basically the data that you will get. Uh, So the file that you record will appear something like this. So you will see there are 8 rows and there are n number of columns. So 8 rows because it has tuned 8 times. There will be basically 8 such patterns. Here somewhere in here there will be hydrogen line. So that's why there are 8 rows, and you see the first 6 columns. They contain basically other information. For example, this is date, then the second column is time, third column is start frequency, fourth is stop frequency, fifth column I'm not sure, sixth column is the bin size. So you can basically ignore all these columns, first 6 columns, and then you have to basically stitch all these rows to make one single plot like this. One row is basic just this portion, second row will be this portion, and so on. So you stitch them and make this plot.
How bad is the gain across the band?
So it can go as low as like 5-6 dB.
No, that's
even
okay.
more.
The sides, of course.
Yeah.
In between?
In between, it's not flat actually. It's I'm not sure exact number, but
But it is what I meaning by eye. What I have seen is, I mean, what I am using at MCL is pretty flat. It's pretty flat is what I would say.
So
I don't
you
think
can,
you need
yeah,
it.
I don't see the need for
Yeah,
going to small portions and stitching.
yeah,
It might be worth, unless one really finds it bad, one first option, first preference can be to use a single
entire.
spectrum,
Okay.
okay, centered at whatever velocity you want.
Yeah.
That will give a better feel for making the measurement than the stitching.
yeah, yeah,
Okay.
Okay.
It will take away the unnecessary detail.
yeah, yeah.
Right.
So 2.5 megahertz one can take in one go, and maybe you record 100 frequency channels. So it means 2 megahertz, and they're using a resolution of 20 kilohertz.
Okay.
It's like
The
100
continuity
that
is
is also-
important for getting a feel for
Yeah.
you know
Yeah.
the noise structure.
Yeah.
There, also the standing waves.
Right.
Okay, all that feel will go away.
Hmm.
Right now, your chopping is actually creating, if the standing waves are after
Mhm.
the conversion, then you will find that we are actually creating replicas of some partial standing wave pattern across this profile now,
Okay.
which had no business being there.
Okay. Okay. Well, that is also possible. It just we just have to.
Yeah, let them view the complete spectrum first, and
Yeah.
if it's really bad in terms of ripple,
Yeah.
then they adopt this strategy.
So in my experience, that has been the baseline has been difficult to correct if I go for one single real-time spectrum.
There you take central 70%.
Huh.
Don't try to fit the edges.
Yeah.
Right.
That I completely
Yeah.
understand your difficulty.
Yeah. So instead of that, I just made it
That's
much
too
smaller
fine.
than.
That's good. Yeah.
Okay. So we just have to change. Yeah, from 80% we put it 30%. So the edge roll off will be
That is fine.
perfect. Right. So you get a plot like this, and yeah, so power that you get from this measurement is in dBm. So you have to convert it into linear power. And your x-axis, you'll have to create the x-axis. You know the start frequency, you know the stop frequency. So you can create the x-axis. You also know the bin size. So this is the plot that you get after the command. So to remove this baseline pattern that you see, uh, what I did was I took one measurement of the ground. I pointed the antenna to the wall, nearby wall. So which will basically give the same pattern without the hydrogen line. Then if I subtract them, I will basically remove the pattern that you see. It requires a little bit of fitting and so on, but that is left to you. It's interesting to explore. And once you get this clean profile of the hydrogen line, then you can fit Gaussians to this line and create a fit and see the residuals. So this is the bare minimum required. You can go much further in this experiment. So for example, you can convert this frequency axis to velocity axis. So you can basically see the relative velocity of these clouds. So you see multiple peaks because of some reason, and you can get velocities of these peaks. So it's a simple conversion. F by Fs, F naught. F naught is your rest frequency of hydrogen line, which is 1420.405 megahertz. F is your x-axis. You know c is a constant. You can convert the x-axis into velocity, and you also need to add a correction factor to this velocity because uh, the Earth is rotating about its axis. It is also revolving around Sun, and the Sun is also moving in the galactic plane. So all these velocities will vectorically add and give you a correction that you have to add to this velocity, which will give you the rest frame velocity of the plot. To get this uh, correction velocity, we have a Python code which will be shared with you. You just have to enter the direction in which you are pointing and the time of your observation, and that should give you this correction velocity. And of course, you will also need the latitude, longitude, and altitude of your observatory, but those parameters are already entered. Yeah, so that is one thing you can do. Other thing you can do is basically convert your y-axis, which is in power, into temperature. So temperatures are basically what we are usually interested in, and to do that, we'll have to use some conversion, and that can be understood in this way. So we'll use what is called the y-factor method or on-off method. So you need two extra observations for this correction. You point it to some blank portion in the sky or just near the zenith. That should give you one temperature reading. So we assume this temperature or the background temperature is at 5 Kelvin, which is basically CMB plus your atmospheric contribution from the atmosphere. So CMB is at 3 Kelvin and atmosphere also adds a little bit of temperature. So we can assume that this is your antenna is pointing to some 5 Kelvin source. Then you point it to a wall nearby. We can assume that is at 300 Kelvin. And that gives you a second reading. So let's say the reading corresponding to this is PS, the measurement, you are measuring power basically. And the reading corresponding to 300 Kelvin is, let's say, PG. So what you can do is you can write this relation. Yeah, but when you point the antenna to a source, it will of course have the contribution from the source, but it will also have contribution from the system itself. So we are assuming a very simple model where your system is also contributing to this temperature. So we'll first have to figure out how much your system contributes to the temperature. And so let's say when you point to the ground, it has contribution from your system, or we call it T radiometer temperature, plus T sky, sorry, T ground. Also, when you point it to the sky, it will have contribution from your system and T sky. So these are the two values that you measured, and these two values you know. We have assumed their temperatures here. You can find out TR. TR is the receiver. Once you know TR, so you can replace one of these sources, let's say T sky, with your observation, T source. And now this is the unknown. All the other values are known. So you can convert it into a temperature scale. There might still be some offset which you can remove by fitting a line to the baseline. Yeah, so this takes care of conversion of power to temperature. So we get brightness temperatures of this line. And there is, I mean, it depends, after that it depends on you how much you want to do. So one can get a rotation curve of the galaxy, and one can get some structural details of the galaxy from this experiment. So that part, I think we can leave to them. Yeah.
I just had one comment when you point to the wall to get the 300 degree Kelvin measurement.
Yeah.
Let them also move the horn distance to the wall a little bit and say that and check that it's not changing. Because the receiver noise itself will get radiated from the horn.
Yeah.
It will bounce and it will form a standing wave of its own.
Right.
Which you don't want to change.
Right. So what we had suggested was to point it obliquely, not directly.
Well, I think they can see the sensitivity of with the distance, so that they are 100% sure.
Sure. So,
Ideally, an absorber will do.
yeah, profiles when you point to different directions, and these Gaussian peaks correspond to the line of sight cutting these different points on the galactic arms. But one point is special, which is so let's say you pointed in this direction, there will be one cloud which will be basically moving in the line of sight of where you are pointing. So this point corresponds to the most redshifted point on the plot. So you choose the point carefully in the plot which is most redshifted, and let's say that this angle, you know, you are pointing the antenna to some galactic longitude. This R0, you know, If you draw a line here, actually this is R, this angle is 90 degrees. So you need to find, yeah, also we know the velocity of the sun here. So the velocity of in this direction, or our antenna in this direction, will be basically sine V naught. Right? And we know this velocity from observation. So that will be, let's say, the source. So you just yeah, to get then the actual velocity, we'll have to subtract this velocity from the observed velocity. So this is the equation for the source velocity. This is the measured velocity, this is the velocity of the sun. And similarly, from geometry, you can also find out R. So you need to plot the rotation curve, you basically need the velocity of the source and the distance of the source from the galactic center. So from here it's easy to, this is 90 degrees, this is L, this is known, so you can find out R. And also V naught is known, you know this angle, you know this component of V naught. You know this from measurement, what you get is a combined relative velocity. So you can basically simplify it in this equation and get, for multiple observations, you can plot these points V versus R for multiple directions. Let's say this is for one direction, you can plot for other direction and so on. You can see how the rotation curve changes. So for fitting and data analysis, you can use any tool that you are comfortable with.
Determination of pointing objects and beamwidth of the 4-meter telescope, which is at the NCLA and RPL Radio Physics Lab. So this is the 4-meter parabolic dish antenna at the RPL in the East Campus, and so tomorrow, meaning each of the days in the morning, then we will basically, you will see that, and when we are there, I will explain to you what are the various parts and so on. So, but main thing is that the parabolic reflector is behind, which is this one, and there is something called a feed, which is the equivalent one can think of as a single disc CCD at the focus. So you know that for a parabola, all the rays coming from infinity along the axis will get focused at a point which is at its focus, but again it does not produce what you call as like a point source or point object there, the meaning not point object but a point the source there. It has a pattern. So those patterns basically is something which will be there, meaning I would talk a little bit more on that. This is the horn antenna which is on the Ayuka rooftop, meaning this anyway you were using for the H1. So in solar observations, there are two aims. One is the first thing is the find offset between astronomical array deck, which is converted to local azimuth and altitude coordinate system using sun as a radio source. So this is the offset. The offset comes because what we call as the direction, which is at a particular altitude and azimuth, a sun is expected on a particular date at a particular time. You point the telescope according to your encoder, which basically shows you what is the present elevation and azimuth of the telescope. You point, you should get a peak there, but you don't. And that is because what is the coordinate system we are using, based on that, it is not being accurately done. That means when you call as azimuth is say 30 degrees, it is not 30 degrees. Suppose there is an offset of for 5 degrees, so it becomes 35. So like that. So that is the way. The second thing is to estimate the beamwidth of the 4-meter antenna, which is basically effectively comparable to resolution of the telescope. Okay, of course you will need to do that. That is the offset. You will also need ephemeris like either whatever stellarium or X ephemeris or nautical almanac, whatever, to find the location of meaning expected value of the azimuth and altitude of the sun given our latitude longitude. You would like to, you may want to be also interested or reading a bit about to understand how to compute between RA depth, azimuth, altitude, and so on. You should also read a little bit about what is called 3D trigonometry, three-dimensional geometry rather. So how the altitude and azimuth system, zenith, this is meridional plane, so on. So there are some multiple books, either from I would say amateur astronomy or from the meaning 3D, the geometry. You can read from there. This coordinate conversions. So this is basically the celestial equator shaded, and then afterwards ground plane is this one. That is the pole star direction. This is the local zenith. RA is equal to 0, meridian or prime meridian, right ascension, and the declination, how it translates. So this is the formula which basically connects it. But again, nowadays many people would prefer using the computer to find out directly. But ideally, you should know how this conversion is done. And if you go through the meaning, if some of you are interested, one can even in principle can check the derivation either in the net or in the books that how these formulas come in. But basically, this is the way altitude and azimuth is linked to the local latitude and longitude and hour angle of the source, and the declination and RA, of course. There are one books using the already mentioned here, derivations using spherical trigonometry by Smart. This one book used to be there. I think it is there probably in both in IUCAA and NCR library. I hope so. In NCR library it used to be there, and it should be possible for you. Suppose you want to access the library once you get an ID card, it should be possible to go inside in the daytime and access the library if some of you are when you have time basically. Now this again, you are not going to use the same setup, right? You are using RTL dongle, so there is no point going about. No, this I don't want to do. I will skip from this. That one of the main aim of the telescope. Now this is a background, little bit of background I wanted to give, and that background is basically that the aim of a telescope is to increase. One of the aim is to increase the signal intensity received from a space. Now the telescope used in radio astronomy could be of different types. For example, one is which we are already discussing, that is parabolic reflector, which focuses the electromagnetic signal from faraway objects at its focus. You could also use a different type of this thing of telescope, which is basically a combination of conductor wires called antennas, which increases the signal strength due to resonance of incoming radio waves on the antenna. So, for example, a basic example of it is a dipole antenna, where basically it is a lambda by 2 dipole, and you can have voltage resonance or current resonance depending on how it is. But remember that the energy which is concentrated or being acquired by a dipole antenna, for example, is of the order of lambda. So that works well when the lambda is large. For example, you are observing at say 10 meter wavelength, then that itself will give you a collecting area of the order of 100 meters square. So that itself is a good antenna. Okay. So if you are observing at 10 meter, so a 5 meter long antenna. Now, of course, people don't observe at those long wavelengths because you will be affected by a lot of RFI, radio frequency interference, and so on. But yeah, if you are really in a quiet place, a set of such antennas where you basically acquire the voltage, they are getting amplified. You may not want not just one antenna, you may need a set of antennas kept at certain distances. So these are all basically, that's why I am saying in general, I would say that you don't need always a reflector behind, which is a parabolic dish like in optical, to work in radio in the same way. You can have antennas, which is a combination of wire. Now this will be different sets and so on. So I need not go to there, but you should just be aware that there are at least two types of antennas. One is based on the simple parabolic reflector, Newtonian type. The other is a combination of conductor wires called antennas. Now this 4-meter single dish radio telescope at NCL uses a 4-meter conducting parabolic dish. At the focus, so you saw its photo sometime back, at the focus, the waves meet in phase and then they are converted to electrical signal using something called a feed. Now feed is nothing but, again, there is a small wire inside, but I am not going to the wire again because many of you, I guess, would be uncomfortable with that unless you have done the electromagnetics based on how an antenna works. So in general, you can think of a feed as a equivalent of a single pixel CCD of your camera. Your camera has multiple pixels, but this you are basically using a single pixel for doing that. Now, once the electromagnetic waves from a point source pass through a circular aperture and is focused, it does not produce a bright dot at an image, but rather a diffuse circular disk known as Airy's disk, surrounded by much fainter concentric circular rings. If the smearing of the image of the point source is larger than that produced by the aberrations of the system, that means that, remember that here I am talking about two things. One is the diffraction pattern, and if the diffraction, that is the main lobe or the single point, the lobe where the most of the energy is concentrated, the Airy disk which is called as, is larger than the aberration of the telescope, because no telescope is perfect. Like the parabola, which we are talking of, geometrically it should produce point source. If lambda is infinitesimally small, that does not happen because it will have its own error. Now if those errors predominate, then you are not limited by diffraction, you are not utilizing the telescope at its best. So when you use it at its best, that means if the smearing of the image of the point source is larger, not larger than the produced by the aberration of the system, the imaging process is said to be diffraction limited, and that is the best that can be done with that size aperture. Okay, a circular aperture yields a diffracted Airy disk which involves a Bessel function. Often the reflectivity at the edges of a parabolic reflector used in radio is tapered. Tapered means whatever the reflection, suppose the reflection coefficient is 1 by, theoretically you would expect, near the edge you reduce the reflectivity. So it is not 1, and the whole idea is that it should not suddenly get cut off. Okay, so because it produces its own diffraction pattern, so we would like to reduce that issue. And how to reduce that? There is a very simple thing which people do, because this reflector are all wire made thing. How wire, meaning conducting wires, act as a reflector? Because you will find that anything which is conducting will basically can reflect provided its size is much larger than lambda, that is one. But also there can be gaps. That's why these wires, two wires, when the gaps between them are much less than lambda, they can act as effectively plane. That is the whole idea. And so tapering is done at the edges, you reduce the density of the wires. Okay, so the gaps between the wires are larger. So the reflectivity effectively will go down. So that can be shown. So the diffraction pattern within the central lobe, which is basically this pattern, then so this is the theta versus I, and then so we are talking of a pattern which goes like this, like that. So this is called the main lobe. This is called the main lobe, and maybe at half the point. So suppose this is 1, this is 0.5, is called, this thing is called full width half maximum. Okay, so that is called the full width half maximum. So the diffraction pattern is basically, this is now called the main beam often in the radio astronomy. This is the part. So you should just remember that in various lectures you will find from time to time people may end up using the word called beam. So you will be suddenly, some people may be suddenly lost. What does it mean by beam? Beam is nothing but the diffraction pattern, and now some people may refer the beam as the whole thing, which includes the side lobe. But often people talk about the beam which is the primary beam, which is basically this one, the central lobe, most often. So it depends from that. And what I mentioned here, that due to tapering, now this is not ideally for a circular aperture with uniform the reflectivity would not be exactly the Gaussian, but this part most often can be approximated by Gaussian. That is what I am saying. So if you go too far away, this pattern will still be there. So they are not going away. This is more of an approximation we use, and even for sun experiment, we will assume this pattern is of a Gaussian. So that is the main thing. If you find this kind of a thing at the edges, don't fit it. So you limit the fits up to this. So one of the aim of the experiment is to align the 4-meter telescope at NCR East Campus with the proper alt-azimuth coordinate system, allowing it to be pointed to the given astronomical source. This requires this requires the determining the offset between the electronic reference of the telescope and the astronomical alt-azimuth coordinate system using the calculated offset. So I don't need to go into the basic details. This you were already guessing. What we are doing is basically while observing the sun, the beam is pointed in such a way. The telescope, suppose this is sun here. So this is a sun or star. It is looking at that. But now, suppose I am looking at the star, or the telescope has been tilted. I am looking at the star in this direction. So you will see the sensitivity has gone down. So you will see the same star at different offsets and basically try to plot how the intensity has fallen. So that's all you are doing in this experiment. And then you are basically trying to fit a beam shape, and also since you are writing the angles at various distances. So suppose this is the 1 degree, this is 2 degree, 3 degree, 4 degree, like that. And this will not be exactly given to you by encoder. You may find that the telescope is looking at an angle. This is 100 degree, this is 101 degree, 102 degree, like that. So where your peak is, that how offset is that, meaning how much is the offset between that and the astronomical expectation, is the offset. That is what you are going to do. So I don't need to talk of, because there are too many texts here, which I don't think is good for you. Yeah. So I would basically what we do is typically little bit I will just still say, find out the approximate altitude azimuth of the sun, slew in azimuth plus or minus 8 degrees. And this experiment when you are doing can be done visually, pointing the antenna towards the sun if the sky is not cloudy. So look at the shadow of the feet at the center of the dish, and then rotate the antenna till the shadow is centered approximately. That means the shadow falls on the apex of the antenna, that is at the center. If the sky is cloudy, then the experiment is not recommended, then the following procedure has to be followed. So basically you find out the approximate alt-azimuth of the sun, slewing the azimuth plus minus 8 degrees. I would in fact say, maybe if you are not sure at all, that you don't know the offset, then you have to go even more, because the offset suppose is 10 degree, even plus minus 8 degree is not enough. So you should have an idea. If we don't have an idea, then meaning if you are off by a degree or two, this is okay. So plus minus 8 degrees, otherwise you have to go plus minus 10, 15 degrees. So it depends on that. And then, so first thing is, we will have some idea of what is the offset. So I will tell you if such a situation arises when there is no sun. So then we will do slightly different approach, how much to go move. Then you start rotating the azimuth axis in the opposite direction and starts noting down the azimuth angle and intensity, maybe every 1 degree. So every grid point, so basically you are noting the intensity like this. You note it here, then you note it here, you note it here. So at different offsets, different fixed offsets, you will write down the intensity and the angular offset. And these are being used. We will also be using the RTL SDR dongle, as Ashish mentioned some time back. And they rotate the antenna till you have gone to the over to the other side of the sun by whatever 8-10 degrees. Save the recorded data. Repeat the steps 1 to 5 this time from the opposite direction. Do the same for the elevation scans, plus minus 6 degrees or so. And then to proceed, you can do in various ways. You can log into your own machine and do whatever, or you can do in some other machines also in the institute if that is given for the winter school students. So then you make a table with azimuth angles as noted on your notebook and the corresponding intensity in dB in 2 columns. Convert the second column in dB to linear scale, for example by using a program called awk. So this is the syntax that anyway this will be shared with you, don't need to remember all this. Basic thing is that after this is done, you can then plot the thing and fit the data using a Gaussian function like this. This is a Gaussian function where C is basically the full width of the meaning sigma, effectively the sigma. X is the angle, the unknown angle, and x naught is something which we need to determine, which is the offset angle. And I have also added with that a Gaussian function, something called a constant term in intensity through capital D, which is equivalent of a dart current from the SDR dongle. In principle, you can have a dart current, which you are not subtracting. So if we want to do that, that can be done, provided it stays constant. Okay. So then you are basically fitting that fx, whatever you have decided to the azimuth intensity, which has basically 2 columns. One is in degrees, another is basically the intensity converted from dB to linear scale. So 10 to the power whatever that formula I showed, 10 to the power 0.1 times the gain in dB, and via these the unknown parameters you fit with that. So that's all. So that is what you will be doing. And you can also save the plots, because these plots you should save. So you give an output file name and save it, and that's all you have to do. And you can use, I'm just showing an example using GNU plot. This can be done using some other softwares as well, like MATLAB. There are SciPy, various things you can use for doing the same. Yeah, so that is all the case you have to do. And so maybe with this I will finish. Please feel free to ask questions. Yeah.
Full beam half.
Yeah.
Is it nothing but half power beam?
Yeah, it is basically half power beam. Yes. Anything else?
Sir, like, I don't know if it's basic or not, but so you have explained all the like, how to measure. So, but what is the actual meaning of offset? So, what does offset mean? Like, when we say we are measuring offset, like what we are checking, what we are doing.
No, so the point is, this is something of a basic thing, is instrumental in nature. Any instrument you use has to be calibrated, right? So it is effectively a calibration procedure. So you have assumed that when you are looking at meaning your instrument is telling my altitude is 20 degrees, how do you know it is 20 degrees? It could be 25 degrees. The instrument has wrongly been given the 0 is not 0. So instrumental 0 calculation is just that, nothing else. Yeah. So the zeros are not well determined of a system. That's all.